Well, here we are again for another virtual lab. In this case, we're going to be dealing with rubbing alcohol and salt. Get this show on the road. We're going to start off by talking a little bit about the rubbing alcohol. 2-propanol is the official name. It's a 3-carbon molecule. Here's a 3-dimensional version of it, sp3 hybridized, and we've got prop. Oops, here, let me hold it a little bit better. 3 carbons, 1, 2, 3. The hydrogen's around it. If we had a hydrogen here, we'd have propane, which is a gas at room temperature. But this OH, which is the oxygen and the hydrogen, make this an unsymmetrical molecule that has a negative on the oxygen, a plus on the H, and this is a liquid at room temperature. It boils a little bit lower than water, if I were to put the OH at the end, oops, here we go, it would be 1-propanol. Right now it's at 2. The 2-propanol is a lot easier to make, and it's the more common version. And there's also another reason people like to use 2-propanol rather than 1-propanol. It starts off, when they make this, they make it from petroleum products. In this case, they start off with a propane, and here's a propene, where you've got a double bond on this carbon. They will use some water and react the water with this, and the double bond breaks, and the OH goes right on there. And so we use propane, basically propene, when it has a double bond put on it to make 2-propanol, which is commonly called rubbing alcohol. Back in the 1920s, they had prohibition, and they also had the petroleum industry just really starting to get going, and they found out that this could be used as a spirit of sorts for putting on skin and rubbing, and they'd give massages with it, they'd perfume on it, and the cooling effect as it evaporated very, very readily was supposed to be soothing. And the name is stuck. The U.S. Pharmacopedia indicates that if 70% 2-propanol solution can be called rubbing alcohol. In England, they call them surgical spirits because now its primary use is as an antiseptic and a cleaning agent. This percentage of alcohol and water is really good for getting into the bacteria, protein structures, and breaking it apart. The water sort of opens up some of the proteins, and then the alcohol gets in there and messes them up. So this is a nice combination for, in fact, you might have difficulty getting it now because everybody's concerned about making sure stuff is sanitized, and the rubbing alcohol is in big demand. Oh, another name for it is isopropyl alcohol. When the OH is at the end, it's called normal, when it's 1-propanol. Then this is an isomer of it, and the common name is isopropyl alcohol. And people really should call it propan-2-ol or 2-propanol. Those are the two accepted names for it. But there's our molecule. Well, let's get to the experiment now. We're going to start off by getting 150 mLs of this 70% stuff. I've got my graduate cylinder here, and not graduate cylinder, excuse me, my little plastic beaker with some approximate markings on it. I'm going to fill it up to the 150 ml mark. It's a little bit more viscous than water. It's hard to notice, but it is almost oily, but it evaporates very, very, very well. And it leaves no residue behind. That's why it's used very often as a solvent. And evaporates relatively quickly. Let me see, I'm at the 150 mark. Great. So 150 mLs. Let me spilled a few drops, but this isn't quantitative. The amount, this is just an approximate. After all, I'm using a beaker's markings on it, which are no better than plus or minus 10% at best. So I've transferred my 70% alcohol into here. 70% is about 6 molar. You're going to use a real chemical arrangement. And also, it's a weird percentage. It's a percentage by volume, not by mass. The density of pure isopropyl alcohol is like 0.78. So its density is less than water. So they do it by measuring volumes, which is a little bit tricky. In fact, we'll get into a complication with that later on. Now, I'm going to dilute this a little bit for this experiment. I'm going to put in about 50 mLs of water. So again, I'm going to approximate 40. Oh, 75. Oh, read that wrong. I'm going to have to pour some of this water out. Oh no, I was going to get 75. Excuse me. And I wanted 75. I should have read my instructions that I had down. Make it 75, get it back to where it was. There we are. Yeah, 75 mLs of water. And rubbing isopropyl alcohol, or 2-propanol, and water mix beautifully. In fact, they mix, they're referred to as being miscible, where you can mix them in any proportion and they'll dissolve. I mean, talk about the ultimate of dissolving, dissolvability, if there is such a term. And you've got it there. Let me put the cap on, mix these guys up, and miscible them up, and make sure we've got a homogeneous solution where no little pockets of the rubbing alcohol and water are separated. Give it a little vortex there. Okay, good. That's mixed nicely. The water molecules, here we go, and the OH of the propanol, the positive hydrogen there and the negative here form a hydrogen bonds. Beautifully dissolvable. If they tried to go here, they wouldn't. This is just London dispersion forces. This is where they dissolve. If you have liquid propane, which you'd have to have underneath pressure, you couldn't dissolve much water in it because you wouldn't have this bond. But I mean, it's a great bond for in this case, dissolving, where we have this similar intermolecular attractions. They're strong, and the water can strongly bond to the alcohol. Alcohol can strongly bond to the water. There's really not much preference. And now we've got our mixture. Now we get to the quantitative part. I want to find out the density of this mixture. And I'm going to have an empty graduate cylinder here. This is just nice, dry, empty. Oops, nope. Let's turn our balance on and make sure it sets to 0. I've got a draft screen here in case any drafts come by, and we're at 0, 0, 0. Put the graduate on there and see what we get. Empty graduate. I have my lab sheet all set up with the table done ahead of time. That's kosher, and it helps me take care of things. Here it is, a 7.535 grams. Okay, it's staying stable. That's beautiful. Now let's put 10 mLs of our solution in there. I'll pour it back into my beaker. And get the 10 mLs in. Here we go. 10 mLs, a little stream. It's got a nice little spout. Be a little more careful here at the end. It's a little bit too much. As you can see, I'm way above that 10 ml mark. So my good old pipette bulb. I'm going to hold it up to my eye level. And one more drop. Nope, too much. Still too much. Drop, 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 drop. Drip, drip. Because you can be accurate to about a drop or so, a tenth of a... Oh, I got it. There we go. Bottom of the meniscus is right on that line. I'm not sure how well you can see it there because of the focus, but when you level this out, that bottom of the meniscus, we have a definite meniscus on this, is at that 10 ml mark. So let's see. I didn't get any on the sides. There's no drops hanging anywhere. That we have 10.0 according to this graduate cylinder. And our mass is 16.6 16.665 grams. Read that again, 16.665 grams. And I can find out my grams of solution. You know, I'll get my I can do the subtraction if I wanted here. 0, 3, 1, 9. I'll double check. Alexa, what's 16.665 minus 7.535?
16.665 minus 7.535 is 9.13.
Okay, 9.13. That's what I've got. Grams is how much solution I have. This is 10 ml, so my density is 0.913 grams per ml. This last sig dig is sort of iffy one. The balance only reads a 5 or a 0. So you really, I think this might be valid to 3 significant digits. Now I'm going to check my little graph here. I've got a graph that gives me a density and also a percent by volume. Okay, my percent by volume, 915. Oh, I've got that right on this, 913. It's about 54 to 56% propanol. So I've reduced the amount of propanol in there significantly. And that, if I do a quick calculation, is, let's see, that's about now down to a, let's see, I have a 56, I'm down to about 7 molar. And there we go. I'm not going to pour it down back into the original solution. It's not really considered to be good practice to pour a solution back into your original. You might contaminate it. So I'm just going to leave it just like it is right now. And here I've got my solution that now we know has been diluted quite a bit. And I'm going to add about 59 grams of salt to it. That's way more, I mean, that's quite a bit of salt. We're talking, I think, Alexa, how many tablespoons in 59 grams of salt?
Here is what I found. 59 grams of table salt is equivalent to about 3 1/4 tablespoons of table salt.
Okay, 3 1/4 tablespoons, a good month's supply of salt. Now I made a little paper funnel to get this in there. I just rolled up some paper, cut the end off, and I'm going to dump the salt in here. There we go. You just hear it pouring in there. That's quite a bit of salt. And I'm going to cap it. There we go. Now we're going to have a competition. We've got propanol in there that is attracted to the water molecules. But now we've got salt ions. We've got our Morton kosher salt ions in here, and they're pluses and minuses, and they're going to be attracted to the plus and minus of the water, the very intense plus and minus of the water. And as they do so, because water's got 2 of these, you're going to have the water attracted to the salt more than this propanol, because the propanol's got London forces here. Not nearly as attractive to ions. So we're going to switch from hydrogen bonding between the water and isopropanol to dipole ion attractions between the salt and the water. And that's where the shaking up comes up. I'm going to tighten this up and shake like mad, because I want as much salt to make contact with that water as possible. In fact, what I'm going to do right now is I'm going to set this up so we can see what's happening. I'll shake it up some more and get a black background. Increase our visibility here. And let that salt provide some competition for the miscibility that the propanol used to have. So there we go. Now I'm going to put this and move it over just a touch so you can see it better. And we're going to give it some time lapse. I'll shake it a few times in between, and then we'll come back to it. I'll fast forward through the time lapse to see what ends up happening with this intermolecular competition. Here, shake it up some more and give it a few minutes. Okay, I've shaken it a couple of times. We've given it some time. And right now you can see two definite layers. And you can see some little bubbling here and there as the water and sodium chloride and water molecules get together and squeeze out, quite literally, the propanol, which is less dense than the water. So the propanol is up here, and the water and sodium chloride dissolved are down at the bottom. And you can see a very, very definite interface there. Look at that. That's just amazing. That, in fact, let's see if you can, yeah, you can still see it there. It's focused. The salt water solution at the bottom, the denser one, and then the propanol that has been squeezed out, and now the propanol is sticking to itself. It doesn't have anything else to stick to, and the water there. Now let's see how effective this is by, again, finding some density. I'm going to decant some of that squeezed out, that purified sodium propanol out into my beaker and do a density check. So here we go. I've got this, and I'm going to try and just get that about 10 mLs of that top layer out. There, I think I got 10 mLs. I'll put this back and get my graduate cylinder right here. Now, it's not quite dry. It's got some liquid in it, but you know, drying one of these things afterwards is really, really difficult. So what I'll do is I'm going to pour some of this liquid into here and swirl it around. So my impurity, my previous liquid in there is going to be mixing with this, and I'm going to now dump it out into my waste container that I've got. Here it is. Now the liquid inside here is now primarily my new decanted propanol, and I'm going to pour in, I hope, 10 mLs. I may have to decant a little bit more. We'll see. Oh yeah, I will. So decant time. Yeah, it's separated. So I can get just a little bit more of my ideal salted out. It's a good term, salted out. It's been pushed out by the salt, and see if I can get 10 mLs on the money. I can do it drop by drop, and I'll, yes, level, and let's see what this weighs. Now we know the empty mass of the graduate already. Now last time it weighed 16.65. Oh, got to turn my balance back on and make sure it zeros. And I've got my new one. Now, my empty graduate weight was 7.535. 7.535 grams. My new mass is zeroed nicely now. Let's see. Previously it was 16.665. Now, it weighs less. Lower density isopropanol. This looks good. 15.960. I'll do a subtraction. Alexa, what's 15.96 minus 7.535?
15.96 minus 7.535 is 8.425.
8.425 grams. The density, therefore, of 0.8425 grams per ml. I'm going to write down 8.42, and let's see what that is in terms of percent alcohol. 0.842, 0.845. Oh, we're up to 84% propanol. This is actually more concentrated than the original 70%. According to my table, the percentage 845, 842, so it's actually probably closer to 85%. Is 85% propanol by mass, and probably there's a little bit of salt dissolved in there. I'm sure some sodium ions are sticking to the propanol, so my guess is the density of the propanol is actually even less than that. I'm going to do a double check here. I've got a table, and I'm up to about 11 molar. So that's 11 molar propanol at the top, and then we've got our dense salt water solution at the bottom. Let's have a little bit of fun here. I'm going to drop in a whole piece of plastic, a little plastic boat. Voila! And there you can see the boat is floating on the dense alcohol, a dense salt water, and sinking in our propanol solution. One of the ways that they separate plastics when they do recycling is some plastics or some polymers are denser than others. This is a polypropylene, a low density. This dye is probably made out of polystyrene, which has a higher density, and there, it even sinks into salt water. So if you needed to separate these two plastics, you could use a solution that floats away the stuff that has the lower density. Another little trick with this, which is going to be interesting. Here I've got a permanent magic marker, a permanent marker. Permanent markers don't dissolve in water. They're made of a non-polar dye. And I'm picking it up here, and I'm dropping it into my solution. And now I'm going to do some shaking. Another use of propanol is it gets rid of grease and oils industrially. It dissolves them when water doesn't. And here you've got the permanent marker, which is non-polar. And let me put a white background there right now. I'm going to flip this over. You'll be able to see the coloration a little bit better. The non-polar magic marker dye dissolves in the propanol. So if you want to get rid of magic marker, get yourself a high isopropanol mixture, 2-propanol, because look, it's not dissolving in the water. There it is. A little arrangement, and we've got our, that is just amazing. These little molecules and their solubility and intermolecular attractions, wow. And I have an additional show with this, because I've done this experiment a couple of times, more than a couple of times. This is like take 3. I messed up a few times. It's embarrassing, but what the heck? No one's perfect. And let me zoom in. I've got a zoom feature on this camera. And I'm going to zoom in to my, give me a second, a previous mixture I made. There we go. And I got my stir bar. And we're going to do a little bit of spinning. And we'll get that little vortex going. And we're going to pull in some of that isopropyl. There we go. We're not in Kansas anymore. I want to go home. I want to go. There we go. You can click together your ruby slippers and see our little mini tornado made with a propanol solution that has been salted out and a sodium chloride solution there at the bottom. that is, because of the sodium chloride, is preventing the propanol from dissolving. Well, there's our lab. I hope you enjoyed it, and I'll have the data for this available at our at the end of this thing. And hope you learned a little bit about intermolecular attractions, propanol, water, and salt. Goodbye.